Seasonal moving averages are constructed in the same way as seasonal autoregressions. It's easiest to describe a seasonal moving average using the lag polynomial. There are two components to this lag polynomial. There's the first term, 1 plus theta 1L. This is the usual MA1 structure. In particular, we see that 1 plus theta 1L times epsilon t is epsilon t plus theta 1L epsilon t, or epsilon t plus theta 1 epsilon t minus 1. That is, that's a standard MA1. But then, to construct a seasonal moving average, we had an additional term that has a lag set up for the seasonal frequency. Of course, we do the same thing we did in the seasonal AR, that is, we multiply out the terms, and we see we get the similar structure. We get theta 1L, theta m, L to the power m, and then finally we get an additional term, which is a restricted term that is the product of the two previous lag terms. When we put it all together, we see that a seasonal moving average with a first order short run and a first order seasonal term has three terms: epsilon t minus 1, epsilon t minus m, and epsilon t minus m minus 1. It's not particularly common to use seasonal moving averages, or in fact moving averages at all, in forecasting. That's not to say that they should be ex ante ruled out, but the biggest difficulty in using them is that moving averages cannot be estimated by least squares. Prediction intervals in general moving average models are simple to construct. We saw before for autoregressions that when we wanted to construct prediction intervals, we needed to build the MA infinity. Well, here we already have the moving average infinity representation. Of course, it only goes back to Q. We know all terms before Q are 0, and so the exact same structure here can be used. And so when we want to think about the h step error, that is the difference between xt plus h and xt plus h given t, we see that we have the final error, and then we have a number of errors that of course are each multiplied by the moving average terms, because these are exactly the terms that show up in the so-called MA infinity representation of this process. And so when we want to get the variance of the forecast error, we simply have sigma squared h is sigma squared, the variance of the error, and then 1 plus theta I squared for I equals 1 to h to the min of h minus 1 or q. Obviously, once you get past q, there's no further forecast uncertainty. And if we're less than h minus 1, then we only have a finite number of terms for the moving average. And once you have this, the prediction intervals are simple to construct. They're just the forecast plus minus 1.96 times this sigma h, which is the h period ahead volatility. To better understand how moving averages are related to forecasts, it's useful to have an insight into inverting a moving average. In the course, we looked at inverting an AR into an MA infinity, but we didn't spend a lot of time doing the opposite, which is inverting an MA into an AR infinity. So here, we need to assume that theta 1 in absolute value is less than 1. In the course, we describe this as the invertible range for the moving average coefficient. We can see that that's going to be necessary here, because what we're going to do is we're going to see how an MA1 can be turned into an AR infinity. We'll use this relationship later in the course when we actually try to get some insights into some other models and the structure they use, in particular how a particular forecasting model might be related to an underlying data generating process. So we start with the model, simple MA1, xt equals theta 1 epsilon t minus 1 plus epsilon t. We then use our relationship for xt minus 1, which of course has the exact same structure. Everything backshifted by one observation. What we do is we solve this for epsilon t minus 1 as a function of xt minus theta 1 epsilon t minus 2. We then plug in for epsilon t minus 1. And we see when we go one step back, we get epsilon t plus theta 1 xt minus 1. So now we have an AR1, and we have theta 1 squared times epsilon t minus 2. We can do the exact same thing for epsilon t minus 2. Just convert it to be xt minus 2 minus theta 1 epsilon t minus 3, which we then take and plug in again. We solve out, and we see we get epsilon t plus theta 1 xt minus 1 minus theta 1 squared xt minus 2 plus theta 1 cubed epsilon t minus 3. So we've seen, just going back 2 steps, we get 2 xt's and we get another epsilon t. You could imagine if we continued this, the next term would be going to give you plus theta 1 cubed xt minus 3 minus theta 1 to the 4th epsilon t minus 4. And in fact, we can continue this pattern until the beginning of the sample. If we do that, we can actually write xt as a function of the most recent shock, then a weighted average of all of the previous x's. It does have this slightly strange thing here, which is minus 1 to the I plus 1. This is something that happens because we wrote theta with a positive sign. And so what happens, and you can see that happening here, that we have theta 1 minus theta 1 squared. So we have alternating signs there. And then finally, the last term is what happens to epsilon 0. You can see the most important part is it has theta to the t epsilon 0. So as long as t is modestly large, this term is going to be fairly unimportant. If we assume that epsilon 0 is 0, then we have an AR order t. So in fact, when we want to construct the optimal forecast from an MA1, it's actually equivalent to constructing the optimal forecast from an ART. And this simply is exploiting the relationship that an MA1 can be written as a large order autoregression. The optimal forecast depends on this autoregressive representation here, particularly the one step ahead, depends on the thetas with alternating signs, all the way back to the first x. Of course, as long as theta is not particularly close to 1, many of these terms are going to be extremely small and won't play an important role. But what this shows is that the optimal forecast for an MA1 has 2 features. One, it has terms that decline exponentially as we go back. So we have theta, theta squared, theta cubed. Of course, they do alternate signs as well. That's not particularly important. But it also can be written as only a function of xt. So even though we don't observe any errors, we don't actually need to observe errors. That observing xt is equivalent to observing the same information that we need to see. If you want to do longer horizon forecasts from this model, you simply would recurse the autoregression forward. So for example, x hat t plus 2 given t will be theta times the conditional expectation of x t plus 1 minus theta squared times xt plus theta cubed xt minus 1 minus theta to the 4 xt minus 2, and so on. So the example we've done here has mean 0. It turns out in practice that's not an important limitation because we could use the exact same thought process when there is a mean. So we had a MA1 with a mean. In other words, xt equals mu plus theta epsilon t minus 1 plus epsilon t. Then we can simply do this by subtracting mu from xt. If we subtract mu from both sides, we see obviously we won't have a mean on the right side. We then can produce the optimal forecast from the d-mean data. And then finally, once we have x hat t plus h given t, we then can add to that mu plus x hat t plus h given t. In fact, I think here you can see I call this x tilde hat. And then our final x hat depends on that. So in this lesson, we've seen a few things. First, that optimal forecasts and moving average models only depend on observed data. This happens by inverting the MA into an AR. This property will be used later in the course when we actually look at some specific forecasting models. Second, seasonal moving averages are constructed using the exact same methods as seasonal autoregressions, simply by constructing products of lag polynomials where we have lags both at the seasonal frequency and at the time series frequency. Finally, prediction intervals moving average models are simple and follow the same principle as prediction intervals in seasonal autoregressions. That is, they just depend on the moving average coefficients themselves.